All right, we're going to do the second half of lesson 10.5 today on tangent lines. We're going to add a couple of new ideas to the concept of a tangent line that we worked on yesterday. We'll continue to build on some of the ideas we had yesterday, and those ideas will be added into some of the processes that we use today to solve these different questions. But I mean, the basic idea here is tangent lines are tangent lines. You know, what other kind of things can we do with them? What ideas can we determine and use to help us solve some basic questions? So the first one is to look at a circumscribed angle about a circle. And the reason the circumscribed angle comes up right now is because a circumscribed angle is an angle whose sides are tangent to the circle. So circumscribed means the angle's going around the circle. Okay. So if you look at this example, okay, and look at angle ABC, A and C are points of tangency. So BC is a tangent line to the circle D. BA is a tangent line to circle D. A and C are points of tangency. So we would call this a circumscribed angle because the angle is going around the circle. It's just touching the circle at point A and point C. Okay. Now, there's a special characteristic that we can apply to this concept of a circumscribed angle, and that comes in the form of theorem 10.13. All right. Now, I'm going to show you the definition of the theorem, and then when I show you a diagram and kind of explain it, I think it'll make more sense. All right. So it says if two segments or lines are tangent to a circle, then the circumscribed angle and the central angle that that intercept the arc formed by the points of tangency are supplementary. Okay, let that marinate a little bit. And when I show you this diagram, hopefully that makes a whole lot of sense. All right, so if you look at the first part of the definition, so we got the circumscribed angle. So we got two segments or lines that are tangent to the circle. So here is DE is tangent to the circle, and DF is tangent to the circle. So this is my circumscribed angle right here. All right. Now, if I draw a radius from center G to the point of tangency E, we learned that whenever we draw a radius to a point of tangency, that's got to be a 90-degree angle. We learned that yesterday. Now down here at DF, if I draw a radius GF, that's also got to be 90 degrees. We learned that yesterday as well. All right, so we know that these two are 90 degrees. Now, look at this as a quadrilateral. Look at GEDF, that quadrilateral. What do we know about a quadrilateral's interior angles? Well, they always add up to 360, right? If angle E and angle F are both 90, that's 180 of the 360. That leaves 180 left for G and D to share. So that means G plus D is always going to equal 180 because E plus F equals 180, and all four have to add up to 360. Okay, that's where this comes from. All right, so if we get a circumscribed angle and then we look at a radius drawn to each of the points of tangency, we're going to see that the central angle, which is angle EGF or just angle G, and the inscribed angle D, they're going to be supplementary, which means they're going to add up to 180. And that's the reason why. Okay, so look at an application of this. So here they say we got, they're just going to tell us that the measure of QPR, this central angle, has a measure of 19x plus 9. And the measure of angle S out here, the circumscribed angle, is 10x minus 3. Okay, well, what do we know? We know since SQ and SR are tangent to the circle, that this central angle and the circumscribed angle have to be supplementary. We know that's true. Okay, so we know that angle QPR plus angle S have to equal 180. QPR is 19x plus 9, S is 10x minus 3, that's got to equal 180. 29x plus 6 equals 180, just combining like terms over here. Subtract the 6, divide by 29, and x is equal to 6. Now the question says find the measure of angle S. Make sure we finish the problem here. Angle S is 10 times that x minus 6, or minus 3, excuse me, and 60 minus 3 is 57. So this angle has to be 57 degrees. All right, so that's applying a concept of a circumscribed angle. Okay, now let's look at circumscribed polygons, not just angles, but polygons. Okay, so a circumscribed polygon is a polygon that has vertices that are outside of the circle and its sides are tangent to the circle. So the vertices have to be on the outside of the circle and the sides have to touch the circle, be tangent to the circle. Okay, so if we look at these collection of diagrams here, which one of these diagrams represent a circumscribed polygon? And if they don't, explain. So let's look at the first one here. This is a four-sided polygon, right? So that's quadrilateral. Its four vertices are outside of the circle. Its sides all appear to touch the circle just once, which means they're tangent to that circle. So is this a circumscribed polygon? Yes. Okay. Second one, we got this triangle and a circle. Okay. Is this a circumscribed polygon? To be circumscribed, the circle's got to be inside the shape. This clearly circle is not inside that shape. Okay. In fact, the reason I say it's not is because the vertices are not outside the circle. The vertices are on the circle. They got to be outside the circle for the circle to be contained inside that shape. How about this one? Is this one a circumscribed polygon? Well, this one's a no also. Okay. It said that all of the sides had to be tangent to the circle. This side over here is not tangent to this side of the circle. So this is not going to be considered a circumscribed polygon. Is this a circumscribed polygon? I got 1, 2, 3, 4, 5, 6. What's that make it? A hexagon, I think. So we have a hexagon. All six vertices are outside the circle. It appears like all six sides are tangent to the circle. That's a yes. Is this, this is also a hexagon. Is this one circumscribed? Well, look at the vertices. All six vertices are outside the circle. However, the sides are not tangent to the circle. And since the sides are not tangent to the circle, that is not a circumscribed polygon. And then our last one here, this triangle, that's a yes, right? All three vertices are outside the circle, and we just touch on all three sides. So that is a circumscribed polygon. Okay. So if you were asked to identify these, yes, no, you can see what you're looking for. One common application of a circumscribed polygon is this. All right. So they're giving us this triangle JKL, and they're telling us it is circumscribed about Q. So this is a given. They're not asking, is it circumscribed? They're telling you it is. And because it's circumscribed, you know it's tangent. Each side is tangent to the circle. So side JK of the triangle is tangent at point M. Side KL of the triangle is tangent at point N. And side JL of my triangle is tangent at point T. Now we're asked to find the perimeter of this triangle. So we're supposed to take the length of JK, the length of KL, the length of LJ, add them together. Okay, now we're going to pull an idea from yesterday back into what we're working on. So the first fact we're going to use is what we talked about today. Because this triangle is circumscribed, we know the sides are tangent. Okay, the second fact is what we had yesterday. Because these sides are tangent, we know that a point outside the circle, the distance to the tangent points have to be the same. So the distance from J to M and J to P has to be the same distance. We had that theorem yesterday. So that means if JM is 14, JP is 14. Go up here, the distance from K to M and K to N have to be the same. So if K to N is 7, K to M is 7. Go to L here, L to P, L to N has to be the same. The distance from a point outside the circle to the point of tangencies on the circle has to be the same. So N to L has got to be 11. Okay, so those two theorems allowed us to find all the pieces that we're missing. So the perimeter is going to be JK plus KL plus LJ. So JK is going to be 14 plus 7. That's going to be 21. KL is going to be 7 plus 11. That's 18. L to J is 11 plus 14, which is 25. And our perimeter for this circumscribed triangle is 64 units. Okay. All right. Those are the style of questions that you're going to work on tonight. Okay. Using the idea of a circumscribed polygon and circumscribed angles, along with what we did yesterday. Okay. So your assignment, let's make sure we're getting those things. Let's get those done, get them completed. Remember, we're getting really close to the end here. So, guys, keep working on this, keep getting your work